Okay. Okay, so let's continue again with the elimination reaction. Again, if you look at the book of Solomon's in the 11th edition, elimination reaction is included in chapter 6, but when you go to the 12th edition of Solomon's, the elimination reaction would go to chapter 7. So anyway, it doesn't matter because chapter 7 will still be alkenes. So this is a preparation of our alkenes, but we just have to know that elimination reaction is a competing reaction with a substitution reaction that we discussed. So for chapter 7, of course, I will be using the 12th edition of Solomon's. Of course, you have to update our books, but let's continue discussion with the old 11th edition of Solomon's, the elimination reaction, and what is the mechanism of the elimination reaction? Why would it be a competing reaction for the substitution reaction? But of course, when we go to alkenes and how we would like to prepare alkenes, the elimination reaction will also still be used. So let's just go into the mechanism of the E2 reaction. Since it is an E2 reaction, it means that it is a bimolecular. There are two reagents that the reaction would depend upon. So let's say the reaction of the isopropyl bromide. Ito yung isopropyl. Let's say your isopropyl bromide here and the reaction of ethoxide ion. So this reaction here. So in this reaction, okay, the rate of the equation is dependent on two reagents, your substrate and your base. So there are two reagents that would affect on the rate of the reaction. So any change in the concentration of these two reagents, increasing the concentration of these two reagents would increase the rate of the elimination reaction. So from the reaction order, we can infer that the transition state for the rate determining step must involve. Yes.
Present ka.
Yes.
Makita, ma'am.
Makita, ma'am.
I didn't makita. What about this? Kita na siya?
Yes, ma'am.
Sorry. Okay. So here, let's have an example reaction to illustrate on the mechanism of the elimination E2 reaction. Again, when you say E2, when we indicate 2, it means bimolecular, okay, and E means elimination. So let's consider, for example, the reaction of ethoxide and isopropyl bromide or 2-bromopropane. This reaction to form this product, an alkene and an alcohol and a bromide. So what you see here is that there is an elimination of bromine, and on the adjacent hydrogen, beta hydrogen from the alpha carbon. Alpha carbon is the one that contains your bromine here. So since it is an E2 reaction, okay, the rate of the reaction is dependent on two reagents, both these reactants here, the substrate, and here our base. Okay, so you have your reaction here, rate is equals to the K and CH3, CHBr, CH3, and C2H5. Do you have class after 6? Do you have a class? If not, we can continue for 15 minutes. We just talk on the E2 reaction. Para dili mabitin, why would it become a competing reaction? How different would it be from the substitution reaction? So for the mechanism of the E2 reaction, so our base, again, how do we define our base? A base is a substance that has an electron pair and would donate an electron to a Lewis acid. What is a Lewis acid? A Lewis acid is a substance that accepts an electron pair. Okay, now we look at in here, the attack on the E2 mechanism is different from the substitution mechanism. We don't attack a positive carbon here. Now, what we attack is a positive hydrogen, not the positive carbon. Okay, so how did it happen? So bromine here, having an electron pair, would let's start here. The basic ethoxide ion begins to remove the proton from the beta carbon using its electron pair to form a bond. So why is that? Hydrogen here is adjacent to this carbon here. Ano i-attack niya? Because hydrogen here would become more passively charged, partially positive, because of the electron withdrawing effect of this bromine here. So it draws electron paingon sa iyaha. So hydrogen here becomes partially positive. Okay, so when it becomes partially positive, the base with an electron pair in here tends to attack this hydrogen and to form a bond. Okay, partial bond formation here. Okay, so when it forms a partial bond formation, you actually get a transition state. No, so there is a partial bond formation between the oxygen and the hydrogen, and hydrogen will become partially broken. Hydrogen carbon bond will be partially broken here, and this bond will actually partially form paingon kang carbon and carbon here. Okay, nga naman, because when the base forms a bond with hydrogen, okay, so of course, manubra na siya og electrons, biyaan na ni hydrogen, it will give to carbon, and carbon will form a bond that to its adjacent carbon here. Okay, so this is your transition heat. This is your transition state. I hope it can be heard here. And after that, when the base attacks your hydrogen, there is a double bond formation, and then your bromine from here to here, from your bromine here, it will acquire a partial negative charge in the process, and then it will leave when the bond is formed. So you will get your C2H0 hydrogen bond alcohol, and then you have your bromide here. Okay, so what is the reason that your base would be driven, no, to attack the hydrogen? As I have mentioned, your bromine can be like more of an electronegative atom, a partially electronegative atom. It will have an electron withdrawing inductive effect, no, so it kind of draw electrons paingon sa iyaha, and then carbon withdraw electrons paingon kang carbon, and for hydrogen carbon, the electron density will be drawn towards carbon in such a way that hydrogen becomes partially positive. So when you have a base, instead of attacking carbon here, na siya option nga dili mo attack ang carbon here, na siya option nga mo attack ang hydrogen by virtue of electron withdrawing inductive effect instituted by bromine here. So it will attack here. When it forms a bond, there is a partial bond formation and partial bond breaking between hydrogen carbon and partial bond breaking between carbon and bromine. So the base will attack hydrogen, and the bond in the hydrogen and carbon will be formed between carbon, and when it forms a double bond here, the bond between carbon and bromine will go to bromine. No, it will leave. No, of course, it needs electron pair with it, will leave to form a free ion here. So what you get actually is C2H5OH, K, and bromide here. This is for an E2 reaction mechanism. Okay, again, so I would like to emphasize that when the base attacks your substrate, it does not attack the partially positive carbon, but instead it will attack a partially positive hydrogen by virtue of what we call as an electron withdrawing inductive effect brought by the bromine here. Okay, so bromine being an electronegative atom, it draws electron paingon sa iyaha. Of course, you expect that carbon will become partially positive, but na siya yung mga silingan ng mga carbon here. So it draws electron density also from the carbon to disperse the partial positive charge created by bromine. And when it draws electron density sa yung silingan ng carbon, then the bond also between carbon and hydrogen will be affected, and it will have an inductive effect paingon kang carbon to disperse the developing partial positive charge. So in the end, si hydrogen will also have a partial positive charge. So instead of the base attacking the carbon, it will attack on the hydrogen. So you will have C2H5OH bond formation, and the bond between hydrogen carbon will form a double bond here. When the double bond is formed, bromine will leave as a free ion, and you get a double bond, of course. So in the transition state, no, you have one transition state, one reaction coordinate, and yeah, one reaction, one transition state in the formation of the product. Okay, so that is the basis of the SN2 reaction. How does it attack? Okay, when we study E2 reaction, we can study that further in chapter 7. We shall find that the orientation of the hydrogen atom being removed and the leaving group are not arbitrary, and that the orientation where they are all in the same plane, like that one shown above. Okay, so here you have a leaving group and you have a base and it attacks, no? Okay, here you can have, just like in the SN2 reaction, no, the nucleophile must push out the leaving group from the opposite. So when you have here, the nucleophile will have to attack from the opposite side, no, before to obstruct the proton from the base. So it's anti-coplanar transition state of the alkyl halide. Okay, anyway, we will learn more about this in chapter 7, but that is how the elimination E2 reaction occurs. For the E1 reaction mechanism, we can further go with that, no? What happens is, of course, again, it is a competing reaction. Like for instance, you have a third butyl chloride here, and you have your nucleophile, the nucleophile or your base, no? Majority of the reaction you have here will actually proceeds to the substitution reaction. Of course, when you have a tertiary alkyl halide like third butyl chloride, no, there are two configurations, or there are two kinds of there are two products actually here, because there's 80% C2H5OH and 20% C2H2O. You get two products here. So your nucleophile is C2H5O and H2O. So this is an example of a substitution reaction having here. But again, of course, aside from these two products, when you have water and you have C2H5OH, those are competing reactions. If you have two nucleophiles present in solutions, no, you actually get two products, no, third butyl alcohol and third butyl ether. But again, we have to remember that in the SN1 reaction, you get two configurations, no, the R and the S of this, the R and the S of this, there is racemization. Now, aside from the substitution reaction, there is a competition, there is a competing reaction with that, and that is for the elimination reaction. You will actually get here the halide, the chloride here is eliminated, and the H and hydrogen is removed. You'll get CH2, CH3, CH3 here. But you notice on the percent of the product that is that is being produced rather in the elimination reaction is just 17% as compared to the SN1 reaction. Okay, so even if it's a competing reaction, it's still get our product. But if you want to proceed with elimination reaction, having a particular product in mind, of course, later we'll see the conditions, the reaction conditions in such a way that we'll be able to prefer the elimination reaction. So what is the mechanism for the SN2 reaction? So the initial step for both the substitution and the elimination reaction is, of course, always the formation of a carbocation. And then, okay, so you have your carbocation formed here. I'm already in overtime. Okay, wait lang. You have your carbocation, and of course, your carbocation is being solvated. Then in the presence of your solvent or your, usually your solvent is your nucleophile here. So let's say your OH, your solvent, and can actually form O solvent. And this is for your SN1 reaction. No? It will assist, it will solvate rather the carbocation that's being formed also. In the elimination reaction, okay, this is what happens. No, it assists on the it solvates or it forms a hydrogen bond with the hydrogen of the beta carbon. This is the carbon that beta to the carbon that has the halide here. And since the solvent forms a hydrogen bond with the beta hydrogen, then it will aid on the elimination reaction to have this. Okay. So what is the mechanism? Let's proceed in the mechanism. And the mechanism for that is that first, again, the formation of the carbocation. So our example reaction is the CHACl to tertiary alkyl halide and to form your alkene. No. Again, the first step, similar with the SN1, is the formation of the carbocation. Second is our, what is our reactant here is H2O. Now, since this is an E1, or the rate of the reaction is dependent only on the substrate here. So there's only, it's unimolecular, and the rate of the reaction is dependent only on this one, on the substrate. Okay, the second one is, once you form your carbocation, no, the solvent or our base, okay, H2O with an electrons in it, no, will use its electron pair to form a bond with the beta hydrogen. Okay, beta hydrogen. Why would beta hydrogen becomes acidic again? Okay, because once you form your carbocation, no, your system will tend to disperse this positive charge that's being created. No, how would it disperse the positive charge? By using on the bond between carbon and hydrogen. So in the presence of your base, you can easily abstract the proton here to form HOH here, two hydrogen bonds with oxygen and another bond with hydrogen. So you will use the electron pair to form a bond and that no with a positive charge on the oxygen. Again, you have to remember when oxygen forms 3 bonds with a lone pair, you get a positive charge on the oxygen. When oxygen has 2 bonds with 2 lone pairs, the oxygen is neutral. When you use that 1 electron pair to form a bond, 3 bonds in a lone pair, oxygen becomes positively charged. So when it abstracts the hydrogen, you form a double bond here. You actually get H3OH. So here there's 2 steps again. First is this is here, if you can see under free energy reaction coordinate diagram here, you will see that you have your reactant for the step 1. You have your transition state to form your carbocation here. So product reactant 1 and your transition, your product 1 here, and to produce your product, there is first a transition state. You have first transition state. So step 2 is your product 1 and your transition state you have in here. Okay, so once you have your alkene, and then you have your hydronium ion, okay, you get your hydronium ion and the chloride actually here. It should be 2 process. You have transition state 2 here, and you get your product. Okay, so in the elimination reaction, again, whether it's E1 or E2, the base will always abstract the beta hydrogen, not the positive carbon. Okay, so it will always attack the beta hydrogen. And the same with the SN1 reaction. First is the formation always of the positive carbocation. Again, the basis of your beta hydrogen being protonate, being easily abstracted with the base because of the inductive effect in the SN2, E2, because of the halide to the alpha carbon. And this one, when you have your positive carbocation, there is a mechanism, there is that need that would arise to disperse the positive charge. And one way is to use the carbon hydrogen bond. So use this electron density here between carbon and hydrogen to disperse the charge here. So it's easy for the water here to abstract because it becomes more partially positive hydrogen here. So the base it contains the lone pair can easily abstract the proton. Okay, so that ends our discussion. We're already late, no? I'll see you next meeting. And for the next meeting, we'll be starting with chapter 7. Do you have any questions? Okay, on your, oh yeah, I forgot. I should include problem sets. Now I will upload problem set where you can work on some reactions. And then we'll have a quiz next meeting. Also, what else? Indicate your attendance in the LMS. And if ever makalimot na pag-upload sa inyong, I have to upload it in YouTube again. No? Even if I have uploaded it already in the Google Drive, I think I need to upload it to YouTube. I don't know why I can't open the Google Drive now. I have already converted into AVI, but still not open. I still can't open the Google Drive. So I think I'm gonna use YouTube again. So if you have no other questions, then that ends our session today, and we'll start chapter 7 next meeting. Any questions? Okay, that ends our session today, and see you next meeting.